slowly. Stick a knife inside me and twist it all around. I want love to grab my fingers gently, slam them in a doorway.
Another long title in 4.5, it's modeling data using exponential and logarithmic functions. And basically what we're going to be doing here is working with regression. And regression is a pretty cool process. It's a statistical process for estimating the relationships among variables. So basically what that's going to look like is you're going to be given some data, and we're going to come up with an equation that relates the data or describes the data. And that's a pretty powerful tool that's definitely real world if you're working in the world of science or psychology or anywhere that's looking at data. So, you know, once you plot the data and you find the relationship between it, it could be a linear relationship, or it could be a quadratic relationship, could be exponential, logarithmic, trigonometric. There's all sorts of things it could be. For today's work, we're going to be focusing on exponential and logarithmic. Since that's what we've been working on this chapter, we're going to look at some data that's related to each other exponentially or logarithmically, and we're going to figure out how to come up with the equation that describes that data. So we'll start with this first question about Simone. It's a wonderful name. I did not come up with this question or that name in this question. This is from your book again. I'm taking the questions from the class examples just as I did last video. So it says, Simone, a medical research scientist, is investigating a new bacterial culture which could help strengthen a person's immune system. She isolates 50 cells and records the growth and the number of cells over a period of 5 hours. Her results are shown in the table below. Okay, so at time 0, like when it started, she had 50 cells, right? That's what it says right here. And then she watched it for 5 hours and she recorded how many bacteria there were after each hour. And what we're going to do is we're going to figure out the equation. We're going to use our graphing calculator. Now, we're going to do two ways. The first way we're going to do it is using the TI-83. It's very long, it's very finicky, it's ridiculous to tell the truth. Remember, this thing costs you $130 or something. Then we're going to do it again. We'll do the second question with Desmos. Remember, this is free, and this is easy, and this is beautiful, and this is wonderful, and you can get it on your phone. So this is the preferable method for sure, but because they're so common in BC high schools, I will use the TI-83 as well. So that's what we'll do first. So to do the TI-83 method, there's 4 steps. You have to enter the data in lists. You're going to plot the data as a scatter plot. You're going to calculate an equation to represent the data, and then you're going to graph the curve to represent the data. It's unbelievable how much work this is. So I'm not going to write down all the steps. We'd be here all day. If you are using the workbook that I'm using in this course, if you look at page 226 to page 227, they're going to go into slow detail about how to do this. I'll do this a little bit faster. So the first thing it says is state whether the data can be modeled by an exponential or logarithmic function. Well, we're not going to be able to do that until we get all the way down to step 4. So we're going to do all 4 of these steps. I'm not going to keep jumping back and forth, so I'm now going to go to my graphing calculator, and I'm just going to stay right here for the next 5 minutes or whatever it takes to do this. So let us begin. The first thing to do is to enter the data in lists. Here's how we do that. To access lists, we hit Stat, and then you see 1 is Edit, so hit the 1. And here's our place to enter in the data. We have L1 and L2. In L1, I'm going to put the X data, which was 0, 1, 2, 3, 4, and 5. In L2, we're going to put the Y data, which was 50, 75, 112, 169, 253, and 380. Okay, and we're done that first step. Hey, that's not so bad. You're probably saying, what a whiner Mr. Wadge is. This is fast. Yeah, well, we got a long way to go. Okay, the next thing we're going to do is we're going to plot the data as a scatter plot. And maybe where we'll start for that, well, first of all, we'll get out of here. So we'll go second mode, because that's quit. Doesn't mean quit the whole calculator, it just means quit what we just did. So what we're going to do is we're going to set the window. And if you think of the x's, we started at 0. Why don't we go from -1, just so we can actually see that point, and we could go up to, we're going up to 5, but maybe we want to go a little bit further. Let's go up to 8. Okay, now in terms of y, let's start at 0, and the most number of bacteria we saw is 380, so why don't we put 400 in there for our y max, and that'll do for our window. Okay, now what we need to do is access the stat plot, which is above the y, so we're going to go second y, and you get this stat plot right here, and we'll go to the first one and choose that. And we want to turn it on first of all, so you hit enter. You want it to be on scatter plot, and that is scatter plot there. Don't worry, we're not going to do this other stuff here. This is scatter plot, and it says L1 and L2. Remember we entered data in L1 and L2? So that's perfect because it's drawing from those lists to get its X and Y. So that's great. Hit graph, and we should see, if we've done it, yes, there's our points. There's the one at 0, 1, 2, 3, 4, and 5. Great. So we could actually now, I guess, answer that question. Maybe I'll go back to it right now. If you just look at this data, does that look like it's an exponential function, or does that look like a logarithmic function? Well, you can see the data is kind of moving from quadrant 2 to quadrant 1, and that's very representative of exponential functions. So I'll go back here right now, why not, and we'll write that in here. This looks like an exponential function. And we need to write the equation in the form y equals ab to the x power, or y equals ab natural logarithm x. Well, obviously this is the one we're interested in right here because this is exponential. So we want to come up with an equation that looks like this, a times b to the x. We have to figure out what the a value is and what the b value is. Well, we can't really do that, but our graphing calculator can. So we know it's exponential. What we do is we hit stat. Then we're going to go over to calc, so you have to hit the arrow over to calc. And if you look down here, it has a linear regression, quadratic regression, cubic regression, quartic regression. So far, I don't see what I want. 8 is another linear regression, natural logarithm regression, so we might use that eventually, not today. And here we go, we have exponential regression. So we hit enter. And now we need to tell which list to use, so we have to type L1, comma L2 in here. And L1 is in yellow right there, so it's second 1. Then here's our comma, and then second 2 for L2. And if we hit enter, it gives us the answer. See, y equals a times b to the x, where a is 49.95 if I rounded 2 decimal places, and b equals 1.50. We did it. We have our equation. So let's go enter that data in on our page here. A equals 49.95, b equals 1.50, or just 1.5, which means our equation is y equals 49.95 times, I'll put it in brackets, 1.5 to the x power. This is our equation. Now we want to use that equation to figure out some stuff. So what would be great is if we made the graph a little bit bigger. We want to see when x is 6, and I believe we set our window up to 8, so that's okay. But we also want to see when our bacteria gets up to 1,250, so we want our y to be as big as 1,250. We don't have it there right now. So what we're going to have to do is go back to our window and put the y a little bit bigger. Let's put it up to 1,500, or how about 1,300? That's fine. No, I'll do 500. And if I just graph that, we'll just take a look at it. You can see we still have the points. Now what we want to do though is we want to get the curve on there. So how we get the curve, we'll go to our y equals, and we want to put that huge formula, like basically this formula right here. I could just type it in right there. So that's probably easier just to do that. But let's say you don't want to, you're a little lazy. Lazy, it's actually going to cost you more work here probably. You want to put the data that this calculator already found. So what you do is you hit vars, which stands for variables. You go over to down to statistics, which is number 5. So I'll just click 5 here. Then you're going to scroll over to EQ, so a couple over. I mean, who's going to remember this, right? And you're going to take that first one, and there you go. It's now in there. So if I hit graph, I should get the graph showing up, and it should go right through those points, or very, very close to those points. And that's looking very, very good there. Excellent. So again, what I wanted to know for the next question is determine how many bacteria Simone would expect to see after 6 hours. So in this case, x equals 6, and we want to know what y equals. So you could just put 6 in here and solve 1.5 to the 6th power, get that answer, and then multiply by 49.95. But remember, we can get the calculator to do this for us. We hit second, trace. We want a value, so 1, and we want to know when x equals 6. And when x equals 6, the answer is 569.7. Why don't we just call it 570? So we'll write that in there. 570 bacteria. The other question, when can Simone expect to see 1,250 bacteria? So our y value is 1,250. And literally what you're going to do here is you're going to enter that equation into the graphing calculator. So you're going to go to y equals, go down to y2, so all the way down to there. You put 1,250. That will draw a line where y equals 1,250. We want to see where they intersect each other. I don't really like what that looks like. I think what I might do is go to my window and change my x max to 10. I think I'll be able to see it a little better. Let's try that. This thing's so slow. If you have a TI 84 or 84 plus or some other TI, it's a little bit faster. This is a bit of a drawback to TI 83. There you go. This is the point we want to know right there. So the way we do that is second trace. We're looking for an intersection, which is number 5. There's the blinking cursor thing. I'll move it a little bit closer. I'm using my arrows on my keyboard because it's faster. And I'll move it up fairly close. Doesn't really matter, but I'll just put it right there. Hit enter. Jumps to the other one. Yep, it's definitely the other, the straight line this time. Now it says to guess, so I put it about where I think it is. You don't have to be very exact at all. And I get the answer. When y is 1,250, the amount of time that's passed is 7.94 hours. So 7.94 hours, which, why don't we just round it? It's going to take her 8 hours until she sees 1,250 bacteria. Okay, we have one other question to go. We're going to do this one in about a third of the time because we're going to use Desmos this time. It's so much faster. So the table below shows data for 5 recently discovered fossils. Remember we did a question like this before with carbon dating. So after 425 years there was only 95%, well it's still a lot, 95% of the carbon left in, carbon 14 left in some organism, and it goes all the way down to 10,824 years after it died, and there's still 27% of the carbon 14. Again, we want to say whether it can be modeled by an exponential or logarithmic function. So here we go, let's go to Desmos. And the first thing we have to do in Desmos is we have to enter this into a table. So if you click here, it gives you an option for a table right here. Oh, by the way, you can also cut and paste if you have data from like an Excel or something, but I'll enter it all in. So our first X value is the 95, then it goes to 79. This is right off your page, right? Right off your worksheet. And 38, and then 27. And if I go back to the top, it goes 425, and then 1950. 3191, 8,000, and 10,824. There we go. And the other thing we need to do is we need to change the window. So we go to graph settings. Let's see, our x's go, let's start at 0, or even minus 10 is fine. And we want to go up to 100. That'll fit it all in there. And in terms of their y's, let's start at 0, or negative 6 is fine. And let's go up to, well, it goes all the way to 10,000. Let's go to 12,000. And there you go. There's our points. We have 1, 2, 3, 4. I think the 5th point's underneath here. Yeah, there it is. There's our 5th point. So we have all 5 points there. And what we want to do is we want to figure out whether this is exponential or logarithmic. Well, this time it looks like the data is going from this first quadrant and it's going down, and it would cross into the second quadrant. It comes up. It looks like maybe the y-intercept is the asymptote up there. So this looks like a logarithmic function. And because of that, we're not going to use this, that's exponential, we're going to use this. Y equals a plus b natural logarithm of x. And again, we just need to know what a is and we need to know what b is. So what you're going to do is you're going to enter that into the second function here. But you're not going to put y equals, you're going to put y, and by the way, it's y1, right? You see how it's in the y1 column here? So you put y1, look at Desmos is so smart, it immediately makes it a subscript. You're not going to put equals. You're going to go to this ABC and you hit this right there. And this means regressed against. So y1, this data here is regressed against. And remember, the equation we're interested in is a plus b natural logarithm of x, and again it's x1. So you just hit x1 and there you go. It's done already. All those steps we had to do on the T83 are now done for us by Desmos. It tells us that the A value is 38,067, and it tells us that the B value is negative 8,265.8. And so that's great. Look at the curve goes right through the points, so it looks like we did a really good job. We're ready to write down the equation. So A is 38,067 and B is negative 8,265.8. So if we put it in the equation, we have y equals 38,067 plus negative. Well, plus negative is the same as minus 8,265.8, and then the natural logarithm of x. And that's our equation. Good, we can get these ones done very quickly. If the skeleton of a bison is about 10,000 years old, 10,000 years old, is that an X or a Y? That's a Y. Years is a Y. So if our Y is 10,000 years, we want to know what's the X. So no problem. We go here, we'll go down to our third function, and we'll put in Y equals 10,000. That will give us a horizontal line. We're interested in the intersection. Desmos is so nice, it's so fast. We now have our answer, 29.83%. So 29.83%. By the way, do these last two questions sound familiar? We actually did the exact same question in last day's work, but in that one they gave us the equation. This time we're using this data to generate an equation and then solve the questions. But I think we end up with the same exact answers. Last question, if the carbon dating test indicates that approximately 20.3%, well, percent is the x, so x is 20.3%. We want to know what the y is. We want to know how many years old, or the age of the fragment. So we go to Desmos. We want to know when x, so I could just change this one, x equals 20.3. Now we get a vertical line. Oh, I don't see it. Should I go change the window? Nah, just drag. There you go. Right there. I just can't get over how good Desmos is, and it's free, people. It's free. 13,182 is our answer. So 13,182. We want it to the nearest thousand, so it's approximately 13,000 years. And we are done. Take home message, go with Desmos. Okay? Get that on your phone, people.
Yeah, I won't let love disrupt, corrupt, or interrupt me.